slowly get started. Yesterday was just an introduction to the course and very basics on data communications. Today we're going to talk about protocols, and probably next week we'll talk a little bit more about internet applications. And then the next topic, which will start next week as well, we start to get into the details of, for example, how do you send a signal to transfer data between two computers. But this topic is still very broad, or this lecture is still very broad, and therefore I think some students find it quite difficult to follow because it covers everything and you miss many details. But we'll try and go through it, and if you don't fully understand it after this lecture, then as you start to go into some details over the next few weeks, you'll start to refer back to this and start to make more sense. So the topic is protocol architectures and internet applications, almost two different parts. We'll first look at protocol architectures and explain what is a protocol and what is a protocol architecture. First, a protocol is a set of rules that two or more entities follow in order to communicate. So we have protocols in all parts of life, and we're dealing with protocols for computer communications, or communications between computing devices. When you meet someone and you introduce yourself, you're communicating with them, you usually follow some protocol. It may be informal, but you may say, "Hi, my name is Steve," and then they respond after hearing that message with, "Hi, my name is X," whatever their name is. There's some form of protocol there, is that because after I say, or after I meet someone for the first time, the rule is for me to say hello or hi and then say my name. And when the other person receives that message, the rule that they follow may be to say hello back and say their name. So there are some basic rules there that we use when we introduce ourselves. Of course, there are different sets of rules we may use with different introductions and different cultures. But there are some informal rules there. Same when we have computers that want to communicate with each other, we need some rules that those computers will follow in order to communicate. And those set of rules are what we call a protocol. And we spend a lot of the course looking at different protocols. So the entities involved in the communication, there may be two, there may be more in some cases. There may be one computer to multiple other computers, but we'll focus mainly on the case, or use examples of the case of one computer to another computer, two entities communicating. Of course, when computers do something, they need to be programmed to do it. And therefore, when we specify the rules that they use to communicate, we need to be clear the exact set of rules. When I introduce myself to someone, if I say, "Hi, my name is Steve," or if I say, "Hello, my name is Steve," that person will understand the difference between hi and hello. But with computers, we usually program them to be precise. We say the exact message that it will send to the other computer, the exact set of bits it will send to the other computer. So with any communications protocol for computer communications, we have some syntax of the messages that may be exchanged, the format of the messages or the data blocks that are going to be sent between the devices, the types of messages. And we'll see when we look at protocols plenty of examples of that. So we have some syntax of the types of messages this computer can send to this computer, and similar that can be sent back. And then we have the procedures, or the rules themselves. Those rules must be followed by each entity communicating with that protocol. If this computer wants to send a file to this one, maybe there's a protocol that says the computer initially sends a special message saying, "I want to send you a file." This one responds when it receives that saying, "Yes, you can." And then this one responds with the actual file that it wants to send. And then once it's received, this one sends back an acknowledgement saying, thank you, I've received it. That would be a set of rules, and they would be specified in a protocol. They may not use those informal words, but would have the exact format of the messages sent from one computer to another, and that forms a protocol. The procedures also include timing information, because often we associate some timing of how long something will take. For example, again, let's try my introduction. If I say, hi, my name is Steve, and then he didn't respond in time, I time out and walk away. I don't want to meet this person. He didn't introduce himself. I had a timer running. What I did is I sent a message, hi, my name is Steve, and in my head I started a timer. I will wait for a response for 5 seconds. If I receive a response in 5 seconds, then that's okay. I may follow up with another message. If I don't receive a response, either I will try again or I will give up. In that case, I gave up. I could have tried again and said, hi, my name is Steve. And I'm waiting. And he said, hi, in response. So I received a message back, hi. Okay, so that message, I now look at my rules and say, what do I do when I receive the message, hi? Well, in this case, I say, what is your name? So that's the set of rules that I follow for this introduction. If he sent back, hi, my name is John, then I may have followed a different response. Then I would have sent, okay, what are you studying? What course or what program are you studying? So those are the rules that we use in an introduction. Same with computer communications. A protocol defines the set of rules that the computers use to communicate, including timing information, like how long do you wait before you give up or you try again. This entire course we'll see many examples of protocols. And protocols are being used to achieve some aim of communicating some information. The problem is that data communications is hard, it's complex, and it's very hard to build or to write one protocol that will work for every different scenario. If I want to transfer a file from this computer to this one, I may need one protocol to do that. But if I want to send an instant message to a computer, maybe I'll use a different protocol, because they need different sets of rules. Because we have many different aims, in real life we have many different protocols. And rather than just creating thousands of different protocols, people create them in some structured manner. The idea is, because data communications is hard, it's complex, with any hard problem we can apply the divide and conquer principle. Break it up into smaller problems, find solutions for those smaller problems and bring them together. And that's what we do in data communications. We've got this hard problem of how do you communicate between two computers. We break the many tasks for data communications into sub-problems, and we refer to them as layers, or we'll implement those subtasks in layers. And we'll see a diagram showing layers, but we'll have, say, a top layer which performs some tasks. The next layer performs some other tasks related to communications. The next layer, different tasks. Bring them all together and we can achieve our aim of communicating, say, over the internet. So, and we bring these layers together and we get what's called a protocol architecture. This is hard to, it's a concept, it's hard to see how it's applicable. It becomes much more sense as we go through the individual layers over the next topics. But we'll try to illustrate this with a few more examples. We'll try to illustrate it with an example of a very simple protocol architecture. And then we'll introduce some real protocol architectures. We want to communicate between computers. Let's think of what we need to do to communicate. We need applications. Okay? And applications are normally perform a specific task. I have an application that is used for transferring files, send a file from one computer to another. I have another application for sending messages, emails. I have a different application for accessing websites, web browsing, and so on. We have different applications in data communications. We have computers. Of course, we communicate between computers. Those applications are running on computers, and those computers are connected together via networks. It's a simple view of data communications. So given that, let's try and design a protocol architecture that breaks the tasks needed for communications into 3 layers. One set of tasks will involve protocols that support specific applications. We'll have one protocol for file transfer. We'll use a different protocol for emails and a different one for web browsing. So we'll say we have what's called an application layer, some layer which includes protocols that support specific applications. But when I want to transfer a file, if I send a file, it needs to arrive at the destination as an exact copy as what was sent. If I have a Word document and I send it and what's received is different from what was sent, the person cannot open that Word document. So we need 100% reliability when I send a file. Same when I send an email. I write an email, please give this student an F. If I send that email across the network and there's some errors in the network and it arrives as please give this different student an F, then that hasn't achieved the aim. When you send files or emails or when you access websites, you want what was sent to be, or you want what was received to be identical to what was sent. 100% reliability. So we're going to introduce what's called, let's call it a transport layer, which will include protocols for making sure any data that is sent is 100% reliable. We saw an example of reliability just a moment ago in my communication protocol for introductions. I sent a message, hi, what's your name? There was no response. There was some error perhaps. He didn't receive the message. I retransmitted the message. I sent it again. That's one way to provide reliability. If I send a message and someone detects there's an error, I can retransmit. So what we'll do is we'll have protocols that are specific to different applications, and then let's say there's one protocol that is built for transporting data from one computer to another and making sure whatever the data is, whether it's a file, an email, a web page, no matter what type of data, it's delivered reliably. If there are errors, it will retransmit until they're fixed. So we'll have a layer that deals just with reliable data delivery and call it the transport layer. The other thing we need in a network is some way to send data across a network. That is, my laptop's a source, my computer in my office is the destination. There's no one link between them. The data needs to go from my laptop to some device downstairs, across to a device in the other building, and then up to my computer in my office. That's a network, multiple links. How do I know which path to go? Let's say solving that problem is a role of, let's say, the network layer or the network access layer. So what we do is, for data communications, we break the problems into different subtasks, subproblems, and we create protocols that solve the individual subproblems and structure them in some layered approach. In this simple example, we have 3 layers: application, transport, network access. just look at one of these blocks first. This is a protocol architecture. This diagram, which is just these, is our protocol architecture. It's saying that this protocol architecture has 3 layers. We've given them names: application layer, transport layer, network access layer. It's just a way to conceptualize the difference between the tasks of data communications. And we'll say in the application layer, we have a protocol which is specific for file transfer. We'll have a different protocol for email transfer, and another one for web browsing. Different protocols within the application layer designed for specific applications. In the transport layer, we'll have one protocol which is designed for reliable data transfer. The job of this protocol is to take any data, a file, an email, a web page, and deliver it to the destination computer in a reliable manner. If there are errors, fix them. That's the job of this protocol. In the network access layer, we may have protocols to access specific technologies. We'll see that when we go through the example. We may have protocols here as well. We may have a protocol for routing. Routing is finding a path, finding a route. Find the path from the source computer to the destination computer. That's what a routing protocol does. And we may have other protocols. Say a forwarding protocol. So a protocol architecture, we say, is divided into layers. The layers have responsibility for performing specific tasks. Application layer, tasks related to applications. Transport layer, tasks related to transporting data between computers. Network access layer, tasks related for computers to access the network facilities. Inside each layer, there may be different protocols defined. And a protocol is a set of rules that 2 entities follow in order to communicate. This is just an example of a protocol architecture. We'll see a real one shortly. So this diagram shows 3 computers in our simple network. Here's our cloud, which represents the network. Inside here may be different devices. Maybe this is my laptop, this is the computer in my office, and this is some server in some other room inside campus. And the communications network is made up possibly of a wireless link from my laptop, not a cable, but a wireless link. Inside here is a wireless access point, some other network devices connected together, and eventually there's a link to my office PC via a cable, and maybe a link to the server by another cable. So if I want to, maybe we'll rotate. Now this is, okay, yeah, if I want to access a server, the server is a web server. It has some web pages on it. Here's my laptop. I want to access and view those web pages. So I use an application protocol, and I would use my web browsing application protocol to communicate with the web server. From my web browser, it would use some special messages for web browsing to send to the web server. The special messages may be as simple as I send a message saying get some URL. My laptop sends a message to the server, and that message contains, say, the words get, some URL, get example.com index.html, where the server is serving for the domain example.com. Sends it to the web server. The server understands that message because the server has the application layer and implements the web browsing protocol, as does my laptop. They both, to communicate, they both need to implement that same protocol. And since the server understands, whenever it receives a GET message, the rules it follows are find the file on your hard disk, send that file back. So it sends back the contents of the file index.html. My laptop receives it. It was expecting this message. The protocol was send a GET, wait for 1 minute. If you receive a response, then display that on the screen. Display the contents of this HTML file on the screen. If it didn't receive a response within 1 minute, then it may have displayed an error on my screen, like error, page not found. So that's an example of an application protocol being used between one computer and another. Of course, my laptop may run multiple applications. While on web browsing, I may be transferring a file or sending an email. I may be browsing to the web server on this computer and transferring a file with my computer in my office, the PC in my office, at the same time. So I'd be using the web browsing protocol on my laptop as well as using the file transfer protocol on my laptop. The transport protocol, when we send this request, get this web page, the transport protocol takes that data and sends it across the network to the destination and deals with any errors. If everything's perfect, it sends the data and it's received as is. But if something goes wrong in here, we may send the data and it arrives in error. What is received is different from what was sent. The transport protocol has the job of trying to fix that. If it realizes there was an error at the receiver would send back a special message saying, please send again. The transport protocol would send it again and may repeat that multiple times until it's arrived correctly. So, this transport protocol can be used for any of the application protocols. I send a request for a web page. The transport protocol delivers it reliably to the destination. I send a file using the file transfer protocol. The transport protocol deals with delivering that file reliably between source and destination. So we're dividing tasks between different protocols. Some protocols specific to applications, some are generic and do tasks what many applications need. One way to think about your computer and these three layers, the application layer may be implemented in the different applications. Your web browser, Firefox, implements the application web browsing protocol. Your email client implements the email protocol. The transport protocol is used by many applications. So maybe that's implemented inside your operating system. Your OS has an implementation of this that deals with it for you. Similar as network access, that may be implemented in the operating system and or in the network card, the LAN card on hardware there to send the signals. What else can we introduce here? Addresses. We'll cover addresses in more detail, but simply to communicate with someone else, you need to know their address. In most cases, you need to know the destination address. If I want to send a message to computer A, I need to know its address, some identifier of that computer. So let's say each computer has what's called a network address. The network address of computer B may be B, of computer A is A, and computer C is C. Simple. An address, some identifier. So if C wants to send data to B, it sends data and specifies the destination as B. So the network knows to send it in this direction, not in this direction. So we can deliver to the correct destination. Remember, that's one of our three things for effective communications. Delivery to the correct destination. What else? Accuracy and timeliness. We need to deliver the data to the correct destination, therefore we need some addresses. There may be other addresses as well. My web browser on this computer wants to send to the web server on computer A. I need to know the address of computer A, right? It's A. And I need to know the address of the web server on computer A. Because on computer A there may be a web server and an email server. So there may be different types of addresses, and we'll see in the internet addresses for applications are sometimes referred to as ports, but we'll cover that in more detail later. This is really trying to show that data communications, we break the tasks into subtasks. We implement protocols to solve those subtasks, to implement those subtasks, and we structure those protocols into layers, where the protocols in each layer perform related tasks. Protocols in application layer related to dealing with applications. Transport layer, transporting data across a network. Network access, allowing us to send and forward and route data through a network. And in real-life data communications in the internet, we have protocol architectures, and we'll go through one now. That was just an example trying to quickly illustrate how the layers may relate to each other. Should we say this? This is just illustrating in a little bit more depth. Oh, we'll go through this. We have our web. Let's say this is our web server. It's sending the response, or no, let's say it's the laptop. Here's the laptop, here's the server. The data that comes from the application is the page that we're trying to request. You type in a URL in your web browser and press enter. Let's say that that URL is the data that we want to send to the server. The application protocol takes that data and sends it to the transport protocol inside your computer. This is all inside the laptop computer, just some software. It takes the original data, sends it to the transport layer, and it may include some extra information with the data. It normally will include an address. Who is it going to and who is it coming from? In this case, the to is some application identifier, application address, a port number. Number 2 here, from application 1 on this computer. Transport layer does whatever it needs to do to the data and sends it to the next layer, the layer down below, the network access layer. It takes what was received and may add some extra information, and normally it would need to add an address. Which computer is this data going to? Computer B. Which computer is this data coming from? Computer A. We'll often refer to this as a message or a packet or a frame. A packet is the more common or more generic name. It's a packet of data with some extra information saying where is this data going to and where did it come from. The data is sent through our network. Because the to address is B, the network will deliver that to computer B. Computer B receives the data, removes this extra information, passes it on to the transport layer. The transport layer realizes it was to application number 2 and sends it to application number 2 on this computer, which gets the original data and does whatever it needs to do. And then maybe a response comes back. So this was the process for sending the one message from laptop to server. When the server receives this data, it realizes, okay, someone just requested a web page. I'm going to send back a web page. Who do I send it to? Easy. The person who sent me the request, computer A. It came from A, therefore I'll send a response back to computer A. Just some terminology. We had the data and we added extra information to that data. That extra information are called headers. We have the data and add something to the head of that, a header. We encapsulate that data inside a packet. That extra information may be a source or destination address. It may be other information as well. We'll see plenty of examples of that. Sometimes the header plus data is called a protocol data unit. More simply, a packet of data. Ignore segmentation for now. That's a simple protocol architecture. In the internet, we use a protocol architecture, and that's perhaps the most, or we're going to look at the most commonly used or most commonly viewed protocol architecture in use today, we'll call it the TCP/IP protocol architecture. We've said a little bit before, the internet, originally designed in the US Department of Defense about 40 years ago. There are 2 key protocols used, TCP and IP. In fact, TCP is a name of a protocol in the transport layer. IP is the name of a protocol in the network layer. But we'll see that there are more layers soon. There are other protocols, many others, but we often refer to the protocol architecture using these protocols as the TCP/IP protocol suite, the set of protocols related to the internet communications. It's used in the internet that we use today. There are many different protocols, and there are different organizations that create these protocols. There is no official protocol architecture. There's no official document that says that in the internet, the protocol architecture looks like this. But generally, the most accepted architecture has 5 layers. And that's what we're going to use in this course. You'll see in some textbooks it's slightly different, but we're going to use a 5-layered protocol architecture. So the 5-layered protocol architecture is the TCP/IP protocol architecture, and it's what we're going to base a lot of our work on in this course. Around the same time that people developed the internet protocols, another group, ISO, was developing OSI, a different protocol architecture. It had 7 layers. It had many details. We're not going to go through that. The short thing is that they basically were competing against each other and people went with TCP/IP. Not many people used this different protocol architecture. TCP/IP 1. The ISO OSI architecture is not used in practice today, although some principles are. That's it. That's our 5-layer protocol architecture for TCP/IP. You need to memorize those layers, and over time you'll see different protocols that are used in each of those layers. Some of them you already know, some of them you'll learn about. So at the top, so we have 5 layers. Starting at the top, we have layers dealing with applications, going down to the physical layer that deals with getting bits over a link, over some physical medium. How to take bits, zeros and ones, and transmit them as signals. That's what the physical layer deals with. Here I show just some examples of real protocols which are associated with each of those layers. Everyone knows this one, or has used this one, HTTP. It's the name of a protocol used for web browsing. You may have used FTP for file transfer. It's a file transfer protocol. It performs tasks specific to one application and therefore is part of the application layer. In the transport layer, okay, so let's go from the top down, and I think it's described on the subsequent slides. At the application layer, we have, sorry, let's go from the bottom up, because I think that's what's described in the slide. Physical layer is the lowest layer. This performs tasks that are taking bits, zeros and ones, and transmitting them across links, physical links, wired or wireless. So we may have a physical layer protocol that deals with transmitting bits across an optical fiber, or transmitting to a satellite and down, if we want satellite wireless communications. Depending on the transmission media, we may have different physical layer protocols. The simplest way we can think of it is that if you give the physical layer protocol zeros and ones, it will deliver those zeros and ones as signals to the destination. So that's the very basics of communications, taking bits, sending them as electromagnetic signals. Next layer up, data link layer. Sometimes when we deliver those bits, they will arrive in error. I will send the bits 0, 1, 0. The receiver will receive a signal and think it received 0, 1, 1. We have a bit error. I sent 0, 1, 0. Well, I received 0, 1, 1. The third bit is in error. The data link, one role of the data link layer is to fix those errors. Across the link, make sure the data is transferred correctly. So if I have a link, say a physical cable connecting one computer to another, physical layer will send the signals. Data link layer will make sure that the data is delivered correctly across that one link. It may do other things like include addresses as well. You give an address to the endpoints in that link. My laptop has an address, the other computer has an address. The addresses are defined in the data link layer protocols. These 2 layers dealing with links. I have one physical layer protocol on my computer, and at the other computer, at the other end of the link, I have the same physical layer protocol, and they can communicate. Same with the data link layer. It's about getting data across that one link. If I want to send from my laptop to one device to another computer, I have 2 links. The physical layer and data link layer are only worried about getting it across a single link. We may have separate physical and data link across the second link. The network layer is about getting it the data across multiple links across the network. If I have my laptop connected to one device and then a third destination, a third device, that's a network. Two links, a simple network. The network layer deals with getting data across that network from my computer to the intermediate device to the final destination. And in the internet, the core protocol is IP, the internet protocol. That's part of the network layer. Things like Ethernet, wireless LAN deal with the data link and physical layer. They cover both of these layers. Wireless LAN deals with how do you transmit bits from a computer wirelessly to an access point. The internet protocol deals with how do you get data from a computer across a network, across multiple links. Whether the link is wireless LAN, Ethernet, ATM, SDH, some other technology, the internet protocol deals with getting the data across a network, a set of links. Transport layer deals with getting data between one source computer and destination computer reliably, between processors on those computers. An application may be running on my laptop, running as a software process. The transport layer will get data from that process to another software process on the destination computer. The protocol TCP does those things like fix errors. If the data doesn't arrive correctly, TCP will retransmit and send it again and again and again until the data is delivered reliably. Network layer is just about getting data across a network. We'll see that it doesn't care about reliability. It just tries to send it. If it gets there, good. If it doesn't, IP doesn't care. The task of providing reliability is left to TCP. If it detects that the data doesn't arrive, it will retransmit at the source. Finally, at the top, the application layer is many different protocols specific to the different applications. HTTP is a protocol for web browsing. It's similar to what I drew here. Send a request for a web page, send back the web page. FTP is a protocol for file transfer. Send a request for a file and the server sends back the file, possibly as multiple pieces. SMTP is a protocol for email transfer. SSH is a protocol for securely connecting to other computers. And there are many others. MSN or your instant messaging applications have individual protocols. There are hundreds of protocols. So, the TCP/IP protocol architecture has 5 layers. Bottom is physical and then data link. The bottom 2 deal with communications across a single link. The third layer, the network layer, deals with getting data across multiple links across a network. Transport layer is dealing with getting data between software processors on computers. And application deals with specific things for individual applications. So when you access Facebook, you're using HTTP as an application layer protocol for web browsing. That takes your request for the Facebook web page and delivers it to TCP. TCP provides reliable transfers, so it makes sure that your request gets to the server. IP makes sure that the request gets across the internet. It goes from your computer and eventually arrives at the Facebook web server in the US. And then at the data link and physical layer, we may have different protocols. If I'm using wireless LAN, my laptop to access Facebook, then I will be using wireless LAN to connect to the access point out in the corridor. That access point will use then Ethernet to connect to a switch downstairs, and that will use Ethernet to connect to another device in this building. Eventually it will use different technologies to get to the Facebook server. That's a lot of information, and sometimes it's hard to visualize and see how all these layers come together. Over this course, we're going to go from bottom up. We're going to go through technologies from the physical layer and up until the midterm, the data link layer. After the midterm, look at IP at the network layer, then TCP at the transport layer, and finally finish on some applications just before the final exam. And by the end of the course, you will 100% understand this slide, okay? And the idea of protocol architectures. What have we got? This diagram shows 3 computers, 3 devices in a simple network, the simplest network we can have almost. This source computer, let's say my laptop, the source host, the destination computer where we want to exchange application data with, and an intermediate device called a router here. And this is the typical structure of devices and how they communicate in the internet. With the 3 computers, let's draw them. The source host here, the source I'll abbreviate as SRC, the source. And then we have the router and the destination. 3 computers. And let's say they have connections between them. This one is a cable plugged into the source, connected to the router, and it's using a simple LAN, Ethernet LAN. The same LAN cables that you use every day that are plugged into the back of most computers. Just connecting 2 computers. And the source does not have a direct connection to the destination, only to the router. The router has a connection to the destination. It has a second cable. And let's say, for example, it's using a different technology to connect to the destination. It's over a wide area network. So these are within, say, 10 meters of each other on a local area network. But the router connects to the destination via some telephone line over, say, 1 kilometre. And it's using a technology called PDH. You don't need to know what it is. It's just an abbreviation for some technology for wide area networks. We want to communicate between source and destination, between this computer and this computer. So this shows the details of this diagram. We have the 2 links. Inside the 2 hosts, the source and destination, we have protocols implementing each of the 5 layers. There's a protocol for the physical layer, the data link layer, network, transport, and application. Let's focus on the first link first, from source to router. The physical layer protocol implemented here must be the same as implemented here. PHY is just abbreviation for physical here, the physical layer. The protocol used here must be the same as the other side that it's communicating with. They both need to use the same protocol. In our example, it would be an Ethernet physical layer protocol because the technology they're using across that link is called Ethernet. So the physical layer protocol used by the source and router are the same, and that deals with taking bits and sending as a signal across the LAN cable, the Ethernet cable. And in fact, a LAN cable is copper wires, and you send electrical signals. So there's a certain way to send those signals. When the signals are received, the receiving physical layer converts it back to bits. The data link layer is also related to Ethernet. So we could say the Ethernet physical layer is used here. Ethernet also has a data link layer. And that does things like making sure that the bits are delivered reliably to the other side, assigns addresses to the devices. So the data link and physical layer are dealing with getting across this link in a reliable manner. So we can get bits from here to here. Note that on this link, we use a different technology. So the physical layer and data link layer are different from what's used across this link. The physical layer here and here are related to this different technology. We don't need to know what it is, just give it a name. PDH has a physical layer and data link layer from our perspective. So this would be the PDH physical layer, and so would this. They need to be the same on both endpoints of the link. Same with the data link layer. Together, they deal with getting bits across that link. So we have protocols for getting bits from here to here, and separate protocols for getting bits from here to here by transmitting signals across some link. The network layer must be common amongst those three devices. The network layer deals with getting data from the source via the intermediate devices to the destination. So it deals with, okay, we have data. We can transmit that data to the next device, and the network layer at the next device receives that data and then transmits it again across the second link until it arrives here. So even though we have different technologies for the two links, one's using Ethernet, one's using PDH, the network layer provides the commonality amongst those three computers so that we can communicate between computers using different link technologies but still send data. The network layer normally is IP, the Internet Protocol. So, ignoring the top two, with the Internet Protocol we take some data, the network layer knows how to deliver that across, or through a set of routers, intermediate devices, to the destination. Doesn't matter if we have different link technologies. It doesn't matter if we had 10 routers in the middle. This example has one. We could have another router and another one and another one and then the destination. Same approach would be applied. The network layer is IP, it's the same here, here and here. So that allows us to deliver data across a network from source computer to destination computer. Transport layer, if we can get it across the network, make sure the data is delivered reliably between the source and destination. It takes the data from the application and uses the network layer to send it reliably to the transport layer at the destination. If we send data, actually we send it this way, and this one realizes the data it receives is incorrect. Somewhere there was an error. Then it would send back a special message saying, please send again. This transport layer protocol would receive it and retransmit what it sent previously until it receives the correct data, and then it passes the correct data onto the application. So the transport layer has this role of fixing any errors across the network. And finally, the application layer has tasks specific to the applications. If it's a web browsing application, it does things specific that's needed for web browsing. The thing that you notice here, in a network, when we have multiple computers in a path, multiple links, only at the source host and destination host do we have all 5 layers. At the routers, the intermediate devices, we don't need the transport and application layer because they only perform tasks specific for the source and destination. Those tasks aren't needed to be performed at the router. Therefore, it doesn't implement those protocols. Those 2 slides just describe, hopefully, what I've said about those 5 layers, summarises. Let's move on so we can get in a couple of more interesting examples to finish the lecture. First, there are other protocol architectures. In this course, we're going to focus on this 5-layer Internet or TCP/IP protocol architecture. But there are others. There's a 7-layer OSI model, not used really. There's some older ones. IBM had one. Apple had its own protocol architecture. But now they all use the TCP/IP architecture. There are some specific ones for different purposes. For telephone networks, for mobile phones, there are protocol architectures. So this is not the only one, but it's the one that we're going to use just for this course. Okay. We know what a protocol is, a set of rules to communicate between 2 entities, 2 or more entities. A protocol is implemented either in software or in hardware. A standard is agreed upon rules. Some organisations agree upon using a particular protocol. That becomes a standard. Everyone uses it. Having standards is good for competition and having open markets because I can buy an Ethernet LAN card that works in this computer that's made by company 1. You can buy an Ethernet LAN card in your computer made by company 2. Because they both follow the same standard, they will talk to each other. If we didn't have standards and companies that implement the protocols didn't follow the standards, no one would be able to communicate with anyone else. We're not going to talk much about standards other than say that there are many organisations that create standards. There's a list of some of them that you may have heard of. I'm sure you've heard of ISO. They create standards for communications plus other things. You may have heard of ITU. You would have heard of IEEE. Wireless LAN. You may have seen IEEE 802.11. It's a standard for wireless LANs. 802.11g, for example, or N. Created by this organisation. The Internet Engineering Task Force is another organisation that creates standards, and they created IP and TCP and other Internet protocols. W3C creates standards for XML, HTML, and so on. And there are others. A list of them are on the website. You can link to, you can see their details, but just introduce them. Let's finish on an example or some details and then an example of how does addressing work in the internet. Introduce addresses. In the internet we have computers and we want to allow anyone to communicate with anyone else. If I want to send data to the Facebook web server, I need to know the address of the Facebook web server on the internet. What's the address of the Facebook web server? Well, is it www.facebook.com Well, in fact, that's not the real address of that computer. It has a different type of address. So the computers inside the internet have different type of addresses. Let's look at them. Computers attached to a network via what we call a network interface. Let's say the LAN card in the back of this computer, and we plug the cable in. That's the network interface. We can refer to the LAN card as a network interface card. Same as my laptop, I can plug a cable in for the LAN cable. That card is the network interface card. So we say every computer attached to a network has a network interface. Within the single network, all computers must use the same addressing scheme. They must all understand the addresses used within that network. And inside a local area network, or a single local area network, or a single wide area network, we'll refer to that address as a hardware address. It has different names: a physical, data link, MAC address. Let's generally refer to as a hardware address. But we've already seen, so let's say that this computer has a hardware address, HW, hardware address 1, and this one also has a hardware address, HW2. They're in the same LAN, same network, using the same technology. They would use the same addressing schemes. We have 15 minutes. Can you make sure the air conditioner is on, please? Otherwise, more people will go to sleep. In the same network here, everyone uses the same addressing scheme. Different addresses, but the same addressing scheme, the same format of addresses. In a different technology, a different network, we may use a different addressing scheme. This network interface card has the address A and this one B. This one has HW1, this one HW2. I just use different letters to signify a different type of addressing here than here. Because technologies have been developed over the last 40 or 50 years and they've used different address formats. If I choose this one, then I have to use the address scheme that specifies. So, this computer can communicate with anyone that uses the same type of address that's connected in this network. This computer can communicate with anyone using this type of address, these letter addresses. This one, HW followed by a number. These two cannot communicate because they do not know the corresponding address schemes. This one has the address B, this has the address HW1. They're a different format of address. Maybe, okay, that's enough for now. So, inside a LAN or a wide area network, computers use the same addressing scheme, hardware addresses. To communicate across an internet between LANs and WANs, we introduce another type of address. What do we call it? A network logical address, more commonly in the internet protocol, an IP address. This computer, in addition to this address, has an IP address. And this computer, in addition to address B, has an IP address. And in fact, this router, which has two network interfaces, also has IP addresses. So you'll find in most cases, each device which is attached to a network has a hardware address and a network or IP address. The reason for introducing this IP address is that so devices which use different LAN technologies can still communicate with each other. Even though these two addresses are different formats, they have a common address, an IP address, using the same format. So two different types of addresses, hardware addresses and IP addresses. Let's have a look at some. It describes there some of them. Let's have a look on my computer, the addresses. So on your computer you can usually see the addresses. On my computer I can run a command, it will show. We said that each computer has one or more, has a network interface. This program, ifconfig, shows me the configuration of my interface. IF is short for interface, config shows the configuration of my interface. It actually shows I have 3 interfaces. Ignore this one, this is a special case. This one is an Ethernet interface. Ethernet is the protocol used for wired LAN communications. You plug a cable in, you're using Ethernet. This is my wireless LAN interface, WLAN here. My laptop has 2 network interfaces. I can plug a LAN cable in, or I can use the wireless connectivity. It shows different information, different configuration information about my computer. Notice, what does it show? Hardware address of my Ethernet card. It's this strange address. It's in hexadecimal, 0024.EC. Hexadecimal, how many bits? How many bits is one hexadecimal digit? This is the mathematics I assume you know from other courses. How many bits in one hexadecimal digit? No? No? How many? 4. One hexadecimal digit can range from, what, 0 up to F. 16 possible values. We need 4 bits to represent those 16 possible values. So we say one hexadecimal digit is represented by 4 bits. There are 12 digits here. The addresses are actually in binary, but we just represent them in a different format, in this case hexadecimal, to make them shorter to write down and display. 12 digits in hexadecimal is equivalent to 48 bits, 12 times 4. My hardware address is a 48-bit number, just represented in a nice or a nicer form than writing binary. My Ethernet LAN card has a hardware address, this one. My wireless LAN card has a different hardware address, same format in this case. It's a 48-bit address. Maybe if I had a PDH interface, a different type of device, I would have a different address format, maybe a 16-bit address, different scheme. So we can see the hardware address of our computer or our devices on the computer. Let's see, I'll connect to the wireless network. I just connected to the SIT wireless network, and now let's look again. Run the same command. So I connected to the wireless LAN. Ethernet is the same, still have the same address, that hasn't changed. But now my wireless LAN interface has a second address assigned, an internet address or an IP address. This is the internet, INET, just short for internet or IP address. Here it is, 10.10.3.181. How many bits? All right, that's a bit harder. In the IP address, it's formatted in a human readable form as 4 decimal numbers, where each decimal number ranges between 0 and 255, separated by a dot. So the first decimal number can be between 0 and 255, which is how many bits? How many bits to represent 256 values? 8 bits. 2 to the power of 8 is 256. So 10 in binary would convert to an 8-bit number. And this would be an 8-bit number, 8-bit number, 8-bit number. An IP address is 32 bits in length. An Ethernet hardware address is 48 bits in length. It's just that we often write them in a different format so that easier or shorter to write down. So here's my IP address. Because I connected to the network, I got an IP address so I can send data on the internet. As an aside, this is an IP version 4 address, 32 bits. There's a newer version, IP version 6, which uses this strange format which is 128 bits long. We will not cover that yet. That's just showing that each network interface has a hardware address, and if you're going to access the internet, also needs an IP address. Some of those notes are made here. Some examples of hardware addresses. We saw this 48-bit address. There are others. There are 64-bit addresses for hardware addresses. There are telephone number style addresses, like +66, so on. IP addresses, IPv4 are 32 bits. The newer version are 128 bits, but we're not going to focus on the newer version because it's not used so much. So each network interface usually has 2 addresses, hardware and IP. We're not finished on addresses. So, if I want to send something to the Facebook web server via the internet, my laptop needs to know the IP address of the Facebook server. So the Facebook server is some computer in the US, or is a computer in the US. It has an IP address. If I want to send data to it, I want to request a web page from there, then I need to know its IP address. The way that we know the IP, or the way that we find the IP address of the Facebook web server, is by using the domain name www.facebook.com. There's a mapping from that domain name to a specific IP address. If I know the domain name, I can find out the IP address of that server. So when I type in www.facebook.com, my computer knows the destination domain. It does something special to find out the corresponding IP address for that domain. And now I know the IP address of the destination and can send data to the destination. So really we can think of a domain name as a user-friendly name. The real address we use is the IP address. But I can remember a domain name much easier than I can remember an IP address. Final thing for today, last type of address. We have hardware addresses, IP addresses. We have user-friendly addresses like domain names and email addresses, which really is combined with a domain name. And we have port numbers. Port numbers are used to identify applications on a computer. Where can I draw it? My source is running a web application and a file transfer application. I'm running 2 applications on my laptop at the same time. And the destination is a server, a web server and a file transfer server. I want to send data from my web browser to the web server application. I know the destination IP address. This destination is Facebook. I know the domain name. I'm sitting at the source computer. I know the domain name. From the domain name, I can find the IP address, so I know the IP address of this computer, so I can send data to this computer. But I want to make sure the data goes to the web application, not the file application. And to do that, we have an additional type of address, port numbers, or transport address. Each application is given a port number. The web application may be using port 80, and the file transfer may be port 23. Different applications use different port numbers, and we can identify the destination application by specifying the destination port number. Finish with one last example. If I access on my web browser a website, I go to a website, then I can use different commands to show information about connections or data that I've previously transferred. Sorry, I'll show that in a better format. Okay, it wraps around. All this is showing is the data that I've previously transferred in the last few minutes. I just accessed the Google website. This shows that I've recently sent data from some local address, 10.10.3.181. We saw before that was the IP address of my laptop. The source was 10.10.3.181. This number is the port number of my source application. My web browser had port number 55829. And I sent data to this foreign address, 209.85.175.105. And we can check, we could check, we won't now, that this corresponds to the Google web server, or a Google web server, because I accessed the Google website. And the Google web server, let's say, all right, we had Facebook here, but the IP address of the destination is this. This is the port number of the application at the destination, port 80. Port numbers identify applications. IP addresses identify computers on the network. We'll talk more about port numbers and even the structure of IP addresses when we get to the topics of IP and TCP. We'll see a few more examples maybe over the next few weeks. I think that's a good place to leave, but any questions before we finish? We've got 2 minutes left. You can answer a quiz question about what's the difference between a port number and an IP address. You can answer a quiz question. Draw the TCP/IP protocol architecture, which means draw those 5 layers in the right order with the right names. That's one thing you need to memorize. Application, transport, network, data link, physical. Which layer is dealing with transmitting signals? So try to understand just the basics of the differences between the 5 layers. IP addresses identify computer interfaces on a network or in the internet. Port numbers identify applications on a computer. This computer has many applications running. Port 80 identifies the web server application. Port 23, the file server application. And there may be others. Okay, let's finish for today. See you next week. No. Yes, we will. The mailing list is still not running, so don't worry about that. We'll If you're not subscribed, that's okay. We'll make sure that it's running hopefully next week. So see you next week.